All right, for this activity, we're going to look at stats part 3, which is our measures of spread. And so we're looking at exercise 1. It says that given below are the heights of 30 randomly selected pro football and also basketball players. So looking at our pro football players, you can see all their heights listed there. Again, there were 30 of each. And so what we want to do, it says, is first order their heights. So I'll take a couple minutes and you can order that. And then after you order the football players, then we'll order the heights of the basketball players. Okay, now that they're all ordered, we can calculate our 5-number summary. So remember, for our 5-number summary, we need to be able to find the minimum and the maximum. So those are pretty easy. We have those. So looking at our football players, we have 58 is our, or 58, wow, 5.8, and that should be feet there. And then 6.8 is our maximum. And to find the median, that's the middle of all our data. So if we're taking the middle of those 30 pieces, we're taking half of 30, which equals 15. So we're supposed to look at the 15th and 16th data points here. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it looks like we're at 6.2, 6.3 is really the middle. So we're going to take the average of those. So 6.2 plus 6.3 divide by 2, and that makes 6.25. That's going to be our median for the football sample. To find the first quartile, really that is the middle of that first half. And so if we have 15 pieces of data there, we're going to look right in the middle of that, which would be 7.5, which would actually make it the 8th one. But we could also find it by using that locator. So we know that for a Q1, we're going to take 0.25 of 30, and that equals 7.5, which is what I was just saying. So we'll count up 1, 2, 3, 4, 5, 6, 7.5 makes us right here for our first quartile. And then for the third quartile, it's really looking at the other 15 and trying to find the middle, which again, you could just count 8 from that 6.3, but you can also use the locator, which says we're going to take 0.75. So this is showing that 75% of the data falls below this number here. So 0.75 times 30 ends up being 22.5. So again, we're going to round up to 23. So it will be the 23rd spot, just like 7.5 was the 8th spot. So counting, we already know that that was 15 at 6.2. So 16, 17, 18, 19, 20, 21, 22, 23 is right here at 6.5. That would be our Q3. And that would be 6.5. So if we follow that same exact pattern for looking at the basketball, how we're kind of looking at the max and, the minimum and then our maximum, and we find the middle again the same way. We're going to look at taking the 15th and 16th positions, and when you do that, we're looking at between the 6.5, 6.6 here. You can double check that. And so the median is going to be the average of those two. So we'll take the 6.5 plus 6.6 and divide by 2. That puts us at 6.55 for our median. And again, the quartiles, we're still finding still 30 pieces of data, so we can use the same locators that we had over here, which puts us at this 6.3. You can count that out. 1, 2, 3, 4, 5, 6, 7. It's the 8th one. And then on the other hand, you can go and find our Q3, which is the 23rd position. So this is looking at our first quartile is 6.3. So 25% of the data is below 6.3. And 75% of the data is below 6.7. And next it wants us to calculate the range of heights for each of these. So for the football, we have our range is 6.8 minus 5.8, so that's 1. And for our basketball sample, we have 7 minus 5.8, so 1.2, a little bit bigger range. And it wants us to know how that's represented graphically in the box plot, which is what we're going to draw next. And the range is always the whisker part. Now to calculate the interquartile range, and that is the values between Q1 and Q3, we're going to take, for the football, the Q3 minus Q1. That's the interquartile ranges. So 6.5 minus 6 gets us 0.5. And for the basketball, we're looking at 6.7 minus 6.3, which is 0.4. And what it represents on the box plot is that's the actual ends of the rectangle. Because remember, this interquartile range is really the middle 50% of the data. This is the middle 50% based off of those being those quartiles. So if we go over now and we put the data into the table to kind of visually compare these things, for the football players, we had our minimum was 5.8 and our maximum was 6.8, with our median being at 6.25, trying to write the important pieces here, and our Q1 was 6 and our Q3 was 6.4. So kind of making the rectangle and then our whiskers here. And then for the basketball, we have, it had also a minimum at 5.8, but that one had a maximum at 7. So it was a little wider range. So visually you can kind of see that happening. Now we have for our median, let's remember that really quick. Our median was 6.55 this time, 6.55. And our Q1 was 6.3 and our Q3 was 6.7. So if I draw the rectangle here, you can see the whole thing is shifted quite a bit. And we have our whiskers and our range is just a little bit bigger there. So it wants us to use the graph to compare the two distributions. Again, that IQR, the interquartile range, the box, is shifted further right for the basketball players. And what that means then is that we have 75%, kind of looking, let's look at this, 75% of the basketball players, that's all of this stuff, right? Because that was where our Q1 was. We know that 75% of the basketball players are greater than that 6.3, right? That was their Q1. And then we also know that football players, let's kind of look the other way around here, but the football players, 75% of them are kind of living on this side, which is below the 6.4. So we have that 75% of football players are less than or under the 6.4. So that's some interesting things that you can really see nicely from that box plot. All right, for this next example, they are giving us our data about a number of native plant species on different islands in the Galapagos island chain. So below we have Nate's calculation. So we're going to see what Nate did and see if we can see any errors in his thinking here. So for part 1, it says to sort the data from smallest to largest. So just kind of checking, 3, 4, 7, 8, 9, blah, 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 blah. Yep, it looks like that's good. Just one thing that I want to know is it's, as we kind of start looking at number 2, there's 22 values. So I'm just going to double check that he did account for all of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. We're short a value. So just at kind of a quick glance, see if you notice which one that is. And I actually see right here, there's supposed to be 2 9s. So there should be another 9 in there to get our 22 pieces of data. So then when we get to number 2, so this is good, we're 22 pieces. We just need to make sure that we have that. He was missing the 9, because that will mess up all the median and stuff if you're trying to see what's there, because we'd only have those 21 pieces. And so to find the median, if we're looking at 22 values, we do take 22 divided by 2, which is 11. So this is looking good, the 11th and 12th values in that data set. So when we look at those values, we're going to be focused in on, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11 and 12 is 19 and 21. So that works out. That seems like that's correct. And so then we have that the minimum is 3. We agree with that. That's our minimum. And the maximum is 95. So we're agreeing with that. So we're finding the 5 number summary right now. The median separates the set into 2 sets, each of size 11. We kind of agreed with that, right? So there's 11 data pieces on that side and 11 on that side. So if we want to find the Q1, that's halfway in between that. So if there's 11 pieces here, halfway would be at the 6th position. So 1, 2, 3, 4, 5, 6. That would be the 9. So you kind of had the error because you didn't have that extra 9 in there. So this should be a 9. And then Q3, again, it's going to be the 6th position here. So 1, 2, 3, 4, 5, 6. That's putting us at the 30, which is true. Now you can do it using that formula we used for the locator, 0.25 times, and we have 22 pieces. You can work on that to find the locator for Q1, and the locator for Q3 was 75% of the way. Again, you're trying to make sure that 75% of the data is below whatever you get for those quartiles. But it's nice just to break it apart, and all of that seems on track. So again, because they were missing that 9, they didn't have that piece in there. So 9 is the Q1. So when I look at number 4 here, it looks like he already put the Q1 in the right place on our box plot. So his box plot should have been at the 11. This should have been what he had actually. And so our correction to what he had, so this is Nate, our correction is what he had there originally actually. So our minimum value was at that 3 and our maximum value was 95, and our Q1 was sitting at 9. Our median was 19 point, let's see. Our median was between 19 and 21, yep, so it was at 20. And our Q3 we said was 30. So what he had originally up here was actually correct. He just had the wrong Q1. So this is the correct way that our box plot should look. Now, one thing to notice is all of this space here getting to the 95. And what's happening, because that space is so big, and we can see that 75% of our data is sitting over here, is that we do have an outlier or two. And we can investigate that more. There's actually some formulas that you can use to determine if it's for sure an outlier. We're not going to worry about that too much in this class, but you can kind of see there that, yeah, it's heavily weighted on that left side, and so that 95 seems like it's a little out of place, and we call that an outlier, which is what number 5 says. So say 95, and again, 75% of the data that we had is below 30, which was our Q3. So 95 seems quite far from that. All right, and next we're going to look at these just kind of 5 pieces of data that were chosen from the football players and 5 pieces from the basketball players. And what we want to do is compute the mean and kind of see what happens with that. So when we calculate the mean, remember that's adding up all the data pieces and dividing by the total number. So for the first one, football players, you add those all up, divide, you're going to get 6.34. And for the second one, you're going to get actually the same exact thing. Both of them have the same mean. And so it's kind of interesting that we have the same mean, so it seems like the same kind of center of data. But if you look at the basketball players, all of those are above 6 feet, 6 point something. The pro football players, there's even one that's down to 5'9". So what we want to think about is, are these good representations for our center? And so what we want to do is look at this idea of standard deviation. And so these are the definitions from your book. And we want to think about how spread out the data is, or how different the data values are from the mean. So just a couple things to note: the standard deviation is always positive. It'll be 0 if the data values are equal. It gets larger as data spreads out. Standard deviation has the same units as the original data, and it, like the mean, can be highly influenced by outliers. So after reading about the standard deviation, which data set has a larger standard deviation? That's kind of what I was saying, is that if you look at the football players, you have one that is 5.9 feet and another one that's 6.7 feet. That's a big range compared to when we look at the lowest basketball player is 6.1 and the highest is 6.6. It's a little lower range. So it appears that the basketball players are a little less spread out while the football players are more. So the data set that would have the larger standard deviation would probably be the football players, because based on these examples that we have here, it looks like there is a larger range. And so in order to compute the standard deviation, we want to see how different each data piece is from the mean. So we're going to subtract, then we're going to square the deviations, add them together. We'll divide by n if it represents a whole population, or we'll divide by n minus 1 if it's a sample, which is what we have, a sample. And then we'll square root the result. And so let's see how this looks. So for the football players, again, our mean for both sets was 6.34. So we're going to take each of those data points. So if you can look back, we had for the football players, it was 6.7, 6.3, 6.3, 6.5, and then 5.9. For the basketball players, we had 6.1, 6.2, 6.3, 6.6, and 6.5. And so it says that we want to subtract the mean from each data value. So each of these we minus 6.34. Okay, so I subtracted the mean from all of these and we got the deviations. And so we could try and think about, okay, well, let's see if we add all the deviations together, how much they're kind of off from the mean. But because they're off from the mean in positive and negative ways, we need to consider a way to think about if there's a different way that we could do this. And so that's why you can see in the definition here of how to compute the standard deviation is that you have to first square each of the deviations, then we'll add them together, and that really just gets rid of that negativity. And then you could see later on we'll end up actually square rooting that, and we'll kind of see an average of how they're off from each other. So if we square each of these deviations and then add them together, we end up getting 0.352. And we kind of want the average here, so we're going to divide. Remember, it's going to be n minus 1, so there are 5 data pieces. We're going to divide by a 4, and then we'll end up taking a square root. And it ends up that this is about 0.297. Now, similarly, if we look at the basketball players, again, we're going to take these deviations. You're going to square each one and add them together. It ends up that we get 0.172. We'll divide that by 4 and then take a square root, and we end up that that's going to be about 0.207. So if we're looking at those two results, I mean, the number itself doesn't necessarily say too much, but when you compare these standard deviations, you can see that the number for the football players, the standard deviation, is higher than that of the basketball players. And since it's bigger, it's showing there's a larger spread of the data for the football players. And the smaller number shows that it's less spread out for the basketball players. All right. For our last example here, we're going to go back to those dot plots. We have some California rainfall shown here and Utah rainfall, and it's the dots are each month because we're looking at the average monthly rainfall. And so you can see that it's looking at the total inches, and you can see each dot. Again, there should be 12 of them. So looking at this, which one do you think has the most variation or kind of most spread? Well, we'd probably say California. And one way that we could see it besides like calculating standard deviation is looking at California's range. We have 3.7, the max, to 0 here, the low. So we have 3.7 is the range for that. Now Utah, we have a range looking at its max 2.1 and its lowest 0.7. It's equal to 1.4. So just by looking at the range, you can kind of see that California is more spread out. I mean, they're both are skewed more to the right because more of the data is falling on the left. Remember how that was? So just a little side comment that they are skewed right. But yeah, California seems like it has the most variation. So next it says decide which measure of spread. And so we're talking about the standard deviation that we just learned about, or the IQR. That was the interquartile range. And so in my head, I'm thinking about the box on the box plot. So which one would be best to use to compare the variation in the rainfall? And so kind of thinking about this. So standard deviation, that's how you deviate from the mean. So it's all about what's going on with the mean. The interquartile range is all about middles, right? It's all those medians. Which one is the one that normally throws off your data set? Well, often the mean is not very good if there's a lot of outliers. And so if you look back up at California, it looks like we are skewed to the right. So a lot of our data is sitting over here. So some of these are causing, would cause a big change in our mean. And so since California has a few outliers, I'd say that the standard deviation would probably be a better measure of spread. Next, it says to select the value that best represents the standard deviation for Utah rainfall. Since that data is, it's still kind of spread out. It's got a decent spread out. But I'd say that it would be closer to a 1 because it's not as spread out as California. So I'd say it would be a little bit smaller of a number since not so spread out. That's why I'd pick the littler number. And if it had asked the same question, but with California, I'd probably pick the 2 because it was more spread out.